In X-ray computed tomography, it's standard practice to scan one item at a time and then analyse the data. In this example, we're going to show you how to analyse multiple specimens from a single scan. This is far more efficient time-wise. But it is not straightforward. Scan data, when you want to automate your analysis, has to be very clean and free of artifacts. I'll be showing you what type of artifacts can cause problems for post-processing and how to overcome them. We will be looking at 3 tension specimens which have been scanned using X-ray tomography. We can see in this example that the data looks very clean from the surfaces of each of the components. However, to ensure this is correct, the easiest method is to look at the ortho slices. I will be looking at the ortho slice along the XY orientation. On the ortho slice, we simply move through the image stack, checking for any artifacts. We can see that we have a good contrast of the pores to the matrix material. The data also does not show a lot of noise. This is going to make the post-processing a lot easier and mean that we do not have to use any sort of image filters. I will now show you some examples of X-ray reconstruction artifacts which could cause problems in post-processing before we move on to the actual recipe creation for automated analysis. In X-ray computed tomography, the first reconstruction artifact that we should be considering is the cone beam effect. We can see in this example the cone beam effect starts at the centre of the ortho slice and moves diagonally downwards towards the outside edge. The same can be seen at the bottom of the ortho slice where it starts at the centre and then moves diagonally upwards towards the outside edge. The cone beam effect will be made worse as the X-ray detector moves towards the X-ray source, and it will decrease as the X-ray detector is moved away from the X-ray source. The cone beam effect causes a number of issues with post-processing. We can see here the areas which are affected by the cone beam effect have a darker grey pixel value. These are very similar to the pores within the component which we are trying to analyse. So separating these during the segmentation stage will be very difficult. The easiest solution for this is to remove these affected sections during the reconstruction process. In this case, during the reconstruction process, the slices above this point here shown on the cursor will not be reconstructed, and any slices below this point here will also be discounted from the reconstructed volume. This means that when we look at the final data, we will have reconstructed data which is clear of any sort of cone beam effect, and that will make the post-processing a lot easier, allowing us to automate the analysis. In X-ray computed tomography, streak artifacts cause a particular problem in post-processing. In this example, we can see a streak artifact on the edge of the specimen, and the effect is replicated on the opposite edge. This also occurs for specimens number 2 and number 3. In post-processing, the streaks can give a false edge to the specimen dimensions. The streak artifacts themselves are caused by the projections not perfectly aligning during the reconstruction stage. This can be caused by 2 main issues. The first, the specimen is moved during the actual data acquisition. In this example, the 3 samples were placed onto a stage and glued. As the glue was setting, the samples have moved, and this has caused the streaks which we can see. A similar effect would be seen if we place the samples on a foam. As the samples are being scanned, the foam would change over time, and therefore the sample positions would change, and this would affect the reconstruction afterwards. When samples are secured properly, there shouldn't be any streaks. However, if a fly scan is used. This is where a sample is continuously rotated over 360 degrees during the scanning process and projections taken. Fly scans do not have a very good angular accuracy, and this can result in the projections not perfectly aligning in the post-processing. As such, streaks similar to this may be seen. A solution in this case would be to use a step scan, which has a higher angular accuracy, resulting in less streak artifacts. In X-ray computed tomography, beam hardening is a particular problem. When beam hardening occurs, the outside edge of the specimen will appear very bright, and as you move towards the centre of the specimen, the grayscale values will decrease and then increase again as you approach the opposite edge. When the beam hardening correction has been correctly applied, the grayscale value should be uniform across the specimen. This makes picking out the pores within the matrix very easy. To overcome this problem in this example, we put the 3 samples inside a container. The container acted as an X-ray filter, and we can see here the container appears very bright even though it's the same material as the 3 samples. To separate the container from the 3 samples in post-processing adds another step. To make this easier, the container has been eliminated during the reconstruction stage, meaning that the final reconstruction only contains the air and the 3 specimens. Sample setup in X-ray computed tomography is very important. In this case, we have 3 specimens set up at the centre of rotation for the CT scan. They are also placed in the centre of the container, which is acting as an X-ray filter. This ensures that we have a uniform profile across the specimen for the matrix phase. If the specimens are placed too close to the X-ray filter, then we will have a non-uniform grayscale profile going across the specimen. This is shown in this slide. We can see the effect of the beam hardening along the edge shown by the cursor. The edge of the specimen in this location is very bright, and as we move towards the centre, the grayscale values decrease. This will make post-processing very difficult. If ring artifacts, beam hardening and streak artifacts have been eliminated from the reconstructed data, we also need to think about how do we save the reconstruction itself. In this example, the reconstruction has been saved as an 8-bit file. The dynamic range has also been changed. This has caused a number of issues because we can now see a lot of noise within the air and a lot of dark areas within the actual matrix phase of the components. This is going to make post-processing very difficult. In this example, we can see an ideal X-ray computed tomography reconstruction. The samples are in the centre of the volume. The container wall has been cut out to reduce the post-processing steps. The profile across the component is uniform, and the pores show a low grayscale value compared to that of the matrix phase. The reconstruction itself has been saved as a 16-bit file. 32-bit files also show high quality data. And the dynamic range is appropriate to what we want to look at in the final reconstruction.